Welcome to the second part of workshop 11. We are still discussing multi-branch trees, and we will continue from where we stopped in the previous workshop 11. So a quick recap of the B trees. We can remember that, recall that the B tree is a multi-way search tree with the following properties. One is that the root node has either no children or 2 to m children. And apart from that, the internal node must have between m2 divided by 2 to m children, and between m divided by 2 minus 1 to m minus 1 data items. This m is referred to the order of the B tree. And lastly, all the leaf nodes must be on the same level. Excuse me. So to illustrate what we said in the previous slide, this is a B tree. This B tree is of order 5, and because it is order 5, the number of children each node can contain is going to be 3, from 3 to 5 children. And the number of data items each of these nodes can contain is between 2 and 4 data items. So this is 5 divided by 2. We have 3 here because we sealed the result to get 3. Similarly, for a B tree of order 6, we know that apart from the root node, other nodes we have minimum of 3 children and maximum of 3 children. And each of these nodes should have at least 2 data items and maximum of 5 data items. Excuse me. Another point we have to remember here is that in B tree, each node contains the data item in the node is also the index key. So we did insertion and deletion under a B tree, and we have steps on how we can insert data into a B tree. So for us to insert data into a B tree, we have to first locate the leaf node where the data need to be inserted. Then if the node excuse me, is not full, then the data item is inserted into the node and our insertion operation is completed. Is complete. But if the node is full, then we need to perform the split operation. When split is performed, the middle element is promoted to the parent node. So in a situation where there's no space, where the promoted data item will occupy, then we have to perform the split operation at the root node again, and at the root node, and the middle item is promoted to the next root node, or there'll be a node created for that promoted data item. So for the deletion, we also need to locate the data that we need to delete. Then if the node
that contains the data we need to delete is not leave node, then we have to perform further operation, which is that the immediate predecessor or the successor will be the leave node, which replaces the data item to be deleted. But if the node is leave node, then the element is deleted. Apart from being deleted, we also need to check that the node has the minimum or more than the minimum number of elements that it should contain. So if it has more than the minimum number of elements, then we have to end our deletion operation. But if it does not, then we need to proceed by looking for the adjacent node that will possibly move an item from that adjacent node to replace the position of the deleted node. And if there's no data item on the adjacent node, then we can combine uh, the nodes. And when we combine some more like two nodes, that may result to the reduction in the height of the tree. So there's a question we have here. So do you still remember the insertion and the deletion efficiency? Yes, you remember that the B tree is a sorted multi-search tree. So, and when we perform insertion and deletion, the order, the efficiency is of the big O notation of the order of log n. So still on the recap on assessing node in a B tree. So each node in a B tree is referred to as a block or a page. So, and they are stored in the secondary storage devices or disk. So, and we all know that accessing data at the external storage or the secondary storage is quite expensive. And this is because the time it takes to access the data. So if that is the case, we can begin to think that the fewer nodes we have, the better our operation becomes, because that will reduce the number of times we need to go to the secondary memory to access the nodes. So the key in each node of the B tree are also used as the index. We explained that earlier anyway. Now, so assessing manipulation or manipulating data in B tree requires multi-access to the external storage. How do we improve the efficiency? So we need to improve the efficiency by reducing the number of times we go to access this data. And we can do that by introducing another kind of B tree. So this kind of B tree is the Bx3. So in Bx3, all nodes except the root node must be at least 2/3 full. So if you compare it with the B tree, where we have the node to be half full, you realize that if we have 2/3 full, it will be larger than that of the half full, which we can find in B tree. And that will give us, that implies that whenever we fetch a block from the secondary memory, we fetch more data items, and that will reduce the number of times we have to go to fetch blocks in the secondary storage. So the frequency of splitting is also another way to decrease, which we can use, and that would decrease the B3 decreases the frequency of splitting. And when a node overflows, we split is delayed by redistributing the keys between the node and its siblings. So this is how a split is performed under B3. And when a split is made, it is made on two nodes, and that two nodes will be splitted into three. But in B3, when a split is made, it is made on one node, and that one node is splitted into two. You see, there is a kind of an advantage of using the B plus tree for splitting and that of the B tree. So now let's have an example to illustrate what we have said in the previous slides. For instance, we want to insert 6 into this B asterisk tree. So in this B asterisk tree, pardon me, it seems I've been saying B plus since, but I mean B asterisk tree. So where do we insert 6 into this B asterisk tree? We look at that all the data need to be inserted at the leave node. Then if that is the case, then 6 should be inserted after 5. But if we look at this node, we can see that the node is full. And in that case, we can't insert here. But because we are using B tree, we can still perform this operation. And how do we perform the operation? We can redistribute the data and perform the operation. So what we're going to do is that the node is full, quite all right, but there's a space in the sibling node, which is here. So instead of splitting the node, we are trying to delay the splitting. All keys and the data from this node and the plus the sibling node and the parents are evenly distributed. So we have to evenly distribute all the data items. And when we have fully evenly distributed it, the median key, which is now 10, is moved to the parent node. So after the operation, we're going to have this as our result. And if you look at this, you can see that there's now space in each of the nodes. So it's possible for us to still add more data without splitting data items without splitting. So for another operation which you want to insert, in this case we want to insert 4 into the Bx3. So in this case, this node is full and the sibling node is also full. So what can we do? So what we do is, yes, we know that the node is full and the sibling node is full. A split occurs and a new node is created. Then the key from the split node, its siblings and the parents are evenly distributed across the 3 nodes. So if these 2 nodes are full, then you have to perform a split. But when we perform that split, we will have to evenly distribute the data items from the siblings and the parents node. So the 2 separating data items are put into the parents node. Now see what we're going to have. So if we redistribute all the data, we will realize that we can have 0, 1 to 5 for 6 and 7 to this. At least all of them are 2/3 full. What I mean is that this 6 should be supposedly is here and 16 is supposedly is here. So you have only 2 spaces left in this node and 2 spaces left in this other node. Then the keys are going to emanate from the 2 first nodes. So the first node is the value supposed to be here is 6. We promote it to the parent node. And the value that's supposed to be here is 16. That will promote it to the parent node. This is how we can perform this kind of insertion in Bx3. So for the Bxx3 and Bn trees, we have the increase in the fill factor can be done in a variety of ways. Of some database system will allow the user to choose the fill factor between 0.5 and 1. For a B tree whose node are required to be at least 75%, which is 3:4, full is called a B plus XX tree. So if we want to have any number of NBN tree, then we can use this equation or this formula where we have n plus 1 divided by 2, n plus 1 to n plus 2 full. So that is for B tree are much less used. The B tree are much less used than the B plus tree. So this is because the B plus tree has some advantages over the Bxx trees. We will see some of these advantages in the subsequent slides. So now let's have a look at, so before we go into the B plus trees, let's have a quick recap of a question we asked in the previous lecture, which is what happens if we require all the data in a B tree to be printed out in ascending order. So one way to achieve that is to use the in-order traversal operation. And another way is if we use the B plus tree. So now let's look at the B plus trees. So for the B plus trees, only the leaf node contains the data associated with each key or the index. So that this explains that in a B plus tree, at the leaf node, there is only at the leaf node that we can find the data items. So, but apart from the leaf node, we cannot find the data items elsewhere. So if we compare this with the B trees, we realize that the B tree has a space for, the data item is also the key or the index for the B tree. So in this place also, the leaf node contains the keys and the index or the associated data. And it makes, the leaf node forms a link, a sequential link or linked list. So that making it possible or easier for scanning data in a sequential order. So storage is in external, data are stored in external storage. So in this case, indexing and data storage are separated. Now, let me explain this in a better way. So in the B tree, there is a separation between the index and the data. The data here is the data items. So the index is stored in a separate level, and the data items are stored in this another level. So the data items are located at the leave nodes. So for all the data items that you want to find, search, delete, or insert, you perform all the operations at the leave nodes. So the index are located either at the root node or at the intermediate node. We will see some of the examples and we will understand better what we are talking about. So this is kind of a mouthful, is just exactly what we have explained in the previous slide. So in this part, we are talking about the internal nodes and the root node. So the internal node is the node between the root node and the leaf node. So they contain only the keys. They don't contain the data, and they are used to index the leaf nodes. Sometimes most they are also called the index set. So they are mostly used to index relational database management systems. Now, what efficiency is improved by the B+ tree, and what is the cost? So you can see some of these efficiencies when we go to the second slide. We see the kind of improvement that the B+ tree brings into this operation. Now, this is an example or a figure to illustrate what we are saying. This is just part of a tree, a B+ tree of order 5. So if we look at this place now, we will see that we have the first level, which is this node, and another level, which is this node. Then we have this level, which is the leaf node. So this is the root node. This is the intermediate, or the one that we call the internal node. So in this case, the two are called the index. But this one is the link that contains the keys and the data. So if you look at this place, realize that the key for these two nodes are 11. For these two nodes rather are 11 and 19. So at this point, it contains the keys and the data. So the data are 11, 13, 15, 19, 26. But the keys are the 19 and 11. So, and if you look at it again, you see that they are linked. The data at the leaf node are linked together. Then it says that the B tree consists of an index implemented as a B tree plus a linked list of the data. So this is what it's referring to. And how can you determine the capacity of the B tree of order 100? So each leaf node can contain up to 99 data items. So for level 2, the B tree can store 9,900 data items because we have 10 leaves, and each can contain 99 data items. So for a 3-level B tree, it can contain nearly 1 million data items, and for a 4-level B tree, that one can contain nearly 100 million data items. So this will give you an idea of the efficiency or the advantages of the B+ tree. So can you compare the space consumed between a full B tree and a full B plus tree of the same height. So can you now begin to compare the kind of space that can be consumed between these two? So if you look at this, you see for the second level, we can have nearly we have 19,900 data items. And for the third level, we can have nearly 1 million data items. So, but if you compare it with the B tree, what do you think is going to give you? Yeah, I want you to have you can pause this video and think about this. And if you can't get, if you are not convinced, you can bring your questions to these tutorial sections. So now let's look at how we can insert data into B plus trees. So first we have to check that a new record is need to be inserted at the leaf, which is similar to the kind of operation we would have done in B tree. Then we can scan the index to locate the node. Then if leaf node has space, so as if the leaf node has a space where we can insert the data, then we insert the data, excuse me. Then if we have inserted the data there, we do not need to change the index of the data or the node that we have where we have inserted the data. And we have a question which says, why is it not necessary to change the indexing if the leaf node has space? So if the leaf node has a space already, because for each data item, it needs to have an index to refer to that data for that data item in a node. So if there is an index for the data for that node already, there's no point changing the index value. So, but if there is no index for that node, that is when we can begin to think of finding an index for that particular node. Then let's move forward. So if a leaf node is full, so this is a different condition. So when we insert data and leaf node is full, that means there's no space. Then we need to perform a split. So that split, performing a split, we all know that new leaf node is included in the sequence, and the record or the data are distributed evenly between the new and the old leaves. Then the first index of the record in the second node is copied. Remember, it is copied but not deleted or removed. So it's not the same as the B tree where the index or the data item is removed. In this case, we only copy the first data item in the second node. Then we copy it and promote it to the parent node. And in a case where the parent node is not full, then the key is inserted there and the operation will be completed at that point. Or if the parent node is full, then we need to perform the split again. And the split at this point will be the same as the kind of split we perform in B tree. So this is what we keep doing until there's a space where the promoted data item can be inserted, or until we get to create a new a root node for that data item. Now let's have an example to illustrate what we have just said. So in this case, we just have a part of a B tree, a B plus tree of order 5. So this is given to us and we want to insert 6. Where can we insert 6 here? We can insert at the leaf node, and 6 can be inserted at this particular node. Excuse me. But this node is full already because we can only have 4 data items in a B plus tree of order 5. So if we insert here, then we need to perform a split at this point. So when we insert here, we perform a split, then the split will give us 1, 2, and another node, which is 6, 8, and 10. Then the first data item in the second node will be promoted to the parent node. And this operation will end here. So then let's now have a look at let's have a look at another condition. So for a case where the deletion of a data item does not cause an overflow, then the we delete the record. We have to know that no change are made to the index set. So then if the key of the record, that is of the data to be deleted, is also in the index set, then the record is deleted from the leaf, but the key is left in the index. What is the reason? What is saying is that when we want to delete a data from the leaf, and that later happens to be the same data at the key or the parent node, then we don't need to delete that particular key. And the reason is that the key will still be used to refer to the same node where we have deleted a data item. So if you still have other data items in that node where you deleted an item, a data item, then there's no point deleting the key. So let's have an illustration of what we have just said. So in this case, we want to delete 6, and 6 is here. So when we delete 6, 8 we move here, and 10 we move to this place. Now we still have 8 and 10 in this node, and this node has a reference or index 6. So even when we have 6 here deleted and 6 is at the index, we do not need to delete 6 because the 6 is still referring or indexing a node which still contains some data items. So we perform the deletion, and this is the final operation. Then yes, the 6 remains in the index. Then there is another case where the deletion of the record causes an underflow. So if we have you deleted an item, a data item, and that data item causes an underflow, then we have 2 options or 2 steps we can take. The first step is that the record in the leaf and its siblings are redistributed and the index updated, or the leaf is deleted and the remaining record included in its siblings and the index is updated. So let's have a look at an illustration. So in this case, we want to delete 2, and 2 is here. So if we delete 2, we can see that we will be left with 1. And for a B tree of order 5, the minimum number of data items we can have in a node is 2. So now we only have one. So in this case, what we need to do, we need to perform a further operation as we explained in the previous slide. So what is the kind of operation we need to perform? We need to merge these two nodes. And when we merge these two nodes, we have 1, 8, and 10. So this is the node that we're going to have. And another thing we can do, we will do is that this index at this point does not index any element. So we can delete this index and have only 11 and 19. So this explains the statements we have in the previous slide. Now, in the B3 index file, there are some advantages of indexed sequential files. So, for instance, the B plus tree are often used as an alternative to indexed sequential files. So you realize that all the data are the leaf nodes. So, but this comes with some limitations. So the disadvantages of indexed sequential files is that the performance decreases as file increases or grows. This is because you notice that we do have overhead of a block being created, and as this block as the file keep growing, we keep on creating more blocks. So another thing is the reorganizing of the entire file that is required. And the advantage of the B3 index itself is that the index is done automatically, and that's during insertion and deletion. And when it is done automatically, just with little or small change. And the reorganization of the entire file is not required. So then the disadvantage of the B plus tree is that extra insertion and deletion is because it's one is the extra insertion and the deletion overhead. So like if you perform insertion, you realize that we might need to add the index and the data as well. So this kind of space overhead. So the advantage of B3 outweighs its disadvantages. And this is the reason why it is extensively used in some cases like managing relational database systems. Now let's compare the B tree and the B plus tree. So for the B tree, the key and the data are not repeated. So the key and the data are not repeated. So, but for the B plus tree, we have the key and the data repeated into different blocks. So data stored in all nodes, and in B tree, data can be stored anywhere within the node. But in B plus, the data are only stored at the leaf nodes. So in another thing to compare is that searching takes more time because there is no index, or the index is also the data itself. But in B plus, searching is quicker, and this is because the data is separated from the index. So we can perform deletion of non-leaf node in B tree. And this kind of deletion is complicated and time consuming. But in B plus tree, deletion is simple because we only have to delete data at the leaf node only. So it's also difficult and time consuming for to output sequential list of data using B tree, but it is quicker and easy to output such sequential list, using B plus tree. Lastly, on this slide, we have that the structure and operation are complicated. Yes, of course, so even when we have to perform like deletion, we need to, if the data we are deleting is not at the leaf node, we know that we need to find another data, either from the preceding node or the succeeding node, to replace the data that we have deleted. But in B plus tree, the structure is and the operations are quite simple. Let's have another example of how we can insert data into a B plus tree. So in this example, we want to insert 70 into the B plus tree. So this is a tree of order 5. Okay, so because we have maximum of 4 here. Now 70 will be inserted somewhere. It's not going to be here. It won't be here. Can it be here or here? So now what we can do is that we have to locate the leaf node, which is this place where we can insert 70. And if we insert 70 at this leaf node, what is going to happen? It will exceed the number of data items that are required for this node. Then we have to split the node into two. When we split this node into two, we have 50 and 55 at the first node, 60, 65, and 70 at the second node. Then following the properties, we have to promote the first data item at the second node to the root node. Or where we are why promoting, we are not deleting, we are just copying in. So what we're going to have 25, 50, 60, and 75. If we perform another operation, in this example, we want to insert 795. So we have a node here. We have so many other nodes between these two nodes. Then we have another node and the last node. So 95 will not be here. It won't be here, but it could be inserted somewhere in this node. So we have located the node where we need to insert the data item. Or if we insert the data item there, it will overflow. So in that case, we split the node, and we have 80, 75, 80, 85, 90, and 95. So we need to promote the first data item to the root node, and promoting the first data item to the root node, we have 85. So 85 will cause this root node to violate the properties of a B tree. And excuse me. And because the maximum we should have, the maximum data items we should have here is 4. But at this point we have, when we promote this, we will have 5. So we need to split the root node in order to make it obey or conform with the properties of the B tree. So if we do that, we're going to split and promote the middle element or the middle data item to the root node. So finally, we have this as the final B tree structure.
At this point, we will conclude what we have discussed in this workshop. We have looked at several examples on how to insert and delete elements in B trees and B plus trees. We advise that you go through them and make sure you understand how to perform these operations. We also advise that you go through the exercises and start looking at the examination papers on Moodle. As always, please bring any questions to the drop-in section or during the tutorial section. Next week, we will be talking about the hash table and the heap. Thank you so much and see you in the next section.